This is homework 3, part C. Okay, so if we can imagine a pool, such as this one, where there's water at the bottom here, and nitrogen flowing over top to dry out any moisture that will escape. So we would have a binary mixture of nitrogen and water here in the middle. So we could call from the top of the water to, say that's at a distance L where the nitrogen meets, and there's some membrane here that keeps the vapor from escaping out, caused from the nitrogen. Okay, so in order to proceed with this mass transfer, we need to look at Fick's law, which says that the molar flux of a component is equal to the negative of the concentration times the diffusion coefficient, which is found experimentally for compounds, multiplied by our concentration gradient. And our concentration gradient is just the change in our component, or change in our component fraction over change in position, which we'll say dz. So this concentration, we know concentration is moles over liters, which can be written as N over V for volume. And using our ideal gas equation, PV equals nRT, we could say that if we divide this out in order to get our moles over volume, we'll say that is equal to our pressure over our gas constant times our temperature. So our concentration effectively is equivalent to our pressure divided by our gas constant times our temperature. This concentration represents a total concentration, and we can find this value by adding the concentration of our water vapor with our nitrogen in our binary mixture, which will be our total concentration. So we can write this by up here saying concentration of water, so pressure over water divided by our ideal gas constant, R, times our temperature, and then add that to the same thing for our nitrogen. To give us our total concentration. If we look at our system here, we could say our nitrogen is flowing down while our water is flowing up. Now when the nitrogen reaches the bottom down here, it has nowhere to go because it reaches that liquid water phase, and we are at stagnant vapor pressure, meaning the pressures aren't going to change. So because we are at constant pressure and at steady state, our nitrogen will kind of get stuck in the bottom here. And so we would expect, if we look at this graphically, ooh, that's big. Call this concentration on the y-axis, and then change the position on the x-axis from 0 to L. So we expect our water to decrease in concentration and our nitrogen to increase. To further observe this relationship, let's look at the overall molar flux. So we can use this equation that says the overall molar flux of component 1 is equal to our molar flux from Fick's law plus our mole fraction times the system's overall molar flux. The overall flux can be written as total flux is equal to the flux of component 1 plus the flux of component 2 in a binary system. Now, so because the nitrogen can't get past the water, won't turn into a water phase, it needs to somehow counteract the upward flowing water vapor, so it will flow up as well in the positive z direction. Now, because that will happen, our nitrogen molar flux will go to 0. It will be 0. So essentially, the nitrogen will replace the displaced water. And so if we write out our equation for our total flux on nitrogen, just because the nitrogen is only in vapor here, using our equation here, we can say that our nitrogen is equal to the molar flux of our nitrogen. Oh, wait. Molar flux of our nitrogen plus the component of the mole fraction of our nitrogen as a vapor. So we'll use Y for that, times our total flux, which we said is equal to the total flux of our water plus the total flux of our nitrogen. In which we know the total flux of our nitrogen will be 0. So what we'll be left with is the molar flux of our nitrogen is equal to the mole fraction times the total flux of our water, which makes sense to say that our nitrogen is replacing the displaced water. So moving further with this, with our equation, we can just plug in a bunch of values. So we'll say that our total, we'll say the total flux of our nitrogen is equal to the molar flux of our nitrogen, which, using Fick's law, the molar flux of our nitrogen is equal to the negative of the concentration times the diffusion coefficient times our concentration gradient, so the change in our molar fraction divided by change of position, and then plus our molar fraction of our nitrogen times our overall flux, which we said is equal to the flux of water plus the flux of nitrogen, which goes to 0. Okay, so if we look at an example for this problem, let me draw it out again, just for the sake of it. So we'll have our liquid water, and we'll have our nitrogen flowing over top. So in this example, we'll say the vapor phase of this pool has a height of 1 meter. So we'll say 0 meters at the liquid surface and 1 meter where the nitrogen is flowing. We said temperature is equal to 50 degrees Celsius, and converting them to kelvins, we'll get 323.15 Kelvin. And then the pressure we said has a pressure of 1 bar, which is equal to 1.013 times 10 to the 5th pascals. And for our diffusion coefficient is 10 to the negative 5 meters squared per second. Okay, so in this question, we will solve for the total flux of our water. So we'll write that out. Same thing how we did up here with our nitrogen. We'll say total flux of our H2O is equal to the negative concentration of our our diffusion coefficient, and that'll be multiplied by the change in the vapor phase of the mole fraction divided by our change in position plus water, the vapor phase mole fraction of water multiplied by the flux of our water plus the total flux of our nitrogen, which we know goes to 0. Okay, so in order to continue on with this, we will need to So what we'll do here is we'll move this term to the left. So with that, we'll get total flux over water. We'll factor out, get So we'll say 1 minus the mole fraction of our water is equal to the negative concentration times our diffusion coefficient times our concentration gradient. Okay, so now we will multiply the left side of our equation by our dz and divide the right side by 1 minus our mole fraction. And with that, we'll get the total flux of our nitrogen, or water, times dz is equal to the negative concentration times our diffusion coefficient multiplied by change in our mole frac over 1 minus our mole fraction. So we can also simplify this further by using our relationship earlier, where we said our concentration is equal to pressure divided by our gas constant times temperature. So if we expand this out, we'll get this Okay, so in order to solve for the total flux of our water, we'll need to get rid of these derivative terms, and to do that, we should integrate. So writing out our integration, we'll still need bounds. So our bounds for our z, for our position, are straightforward. It'll just be from 0 to 1. So in order to find the bounds for our mole fraction, we can use a relationship that says the mole fraction of in the vapor phase specifically is equal to the partial pressure of our water divided by the total pressure of the system. So we have our total pressure of the system, is 1.013 times 10 to the 5th. For water, we can use Antoine's equation to find that value, or we could just Google it. Okay, so Googling the partial pressure of water vapor at 323.15 Kelvin is equal to 1.2 times 10 to the 4th pascals. So we can plug that into our equation. And we'll find the molar fraction of our water vapor should be equal to about 0.12. So that'll be the concentration, or the mole fraction of our water at z equals 0, and at z equals 1, we know that so z equals 0, right on top of the liquid water, our mole fraction is 0.12, and then at c equals L, our mole fraction will be 0. So if we write out our integrals here, So we'll take out our constants. So the total flux of our water multiplied by the integral from 0 meters to 1 meter of our change of position is equal to the negative pressure times diffusion coefficient divided by gas constant times temperature of our integral from 0 to 0.12 divided by, say, 1 over 1 minus our mole fraction integrated with respect from our mole fraction. So this will turn into dz will just turn into z, so 1 minus 0, that'll just be 0, I mean 1. So we'll get just the total flux of our water equal to negative pressure times diffusion coefficient over our gas constant times temperature. So 1 over anything will just be the natural log of the denominator. So we'll get the natural log, natural log of the absolute value of 1 minus our concentration of water vapor evaluated from 0 to 0.12. So that will get our total flux is equal to same thing times the natural log of 0.88. Oh, this should be 1. Yeah, wait, no, never mind. .88. So we can plug in our values here, and we'll find that the total flux of our water is equal to our negative pressure, so said 1.013 times 10 to the 5th pascals times our diffusion coefficient 10 to the negative 5th meters per second squared, divided by our gas constant 8.314 joules per mole Kelvin, and our temperature, which we said was 323.15 Kelvin, multiplied by the natural log of 0.88. Okay, so to find units of this, so Pascal's pressure, we know that's force per area, so newtons per meter squared, and the second law of Newton's second law says that force equals mass times acceleration. So this will simplify down to kilogram meter per meter squared second squared. Cancel those. We'll be left with kilograms per meter second squared. So that'll be our first units. Our diffusion coefficient will just be meters per second squared. Our gas constant will just be, in this case, we'll put mole Kelvin in the numerator and our joules, which we said joules will be in Newton meters, and we know newtons as kilogram meter per second squared. This should have been divided by our area too, so wait. Okay, so meters per second squared times meters, so that would just be kilogram meter squared per second squared. So, keep clicking out. Kilogram meter squared second squared in the numerator, and then instead of Kelvin, 1 over Kelvin. So canceling out our terms here. We'll be left with moles per second squared meter squared, and solving for, this will be negative as well, our total flux we should get a value of 4.76 times 10 to the negative 5.